Welcome back, everybody, on our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep from IIT Hyderabad. Before we begin today's lecture, which will be the last lecture of this module, let's have a quick recap of what we studied the last time around. We saw how images have local homogeneities and sharp edges, which means not all pixels are equally important. And CNNs really exploit this through windowing or the kernel activity, where you use the convolution operation to extract certain localized features. This with the concept of shared weights and localized receptive fields. The filters can scan across the image efficiently and give us a very optimal utilization of resources. Then we looked at one of the earliest CNN architectures developed by IBM in 1998 called Linet 5. This was designed specifically for handwritten digit recognition. The architecture had 7 layers, including 2 to 3 convolution layers, pooling layers, and a fully connected layer right at the end. More importantly, it had only 60,000 parameters, which seems like a really tiny parameter space by today's standards. When we compare this with current set of CNNs such as AlexNet, VGG6, GoogleNet, and even these vision transformers, they require almost tens to hundreds of millions of parameters and billions of multiply and accumulate operations. And through this, we saw that while accuracy has really improved, but it has come at the cost of huge computational needs. This is what we will look at in the detail. And so today we will conclude this module as we circle back to the 2 primary questions that we had asked right at the beginning of our study of this module. What were with the 2 big questions? They were, why was there an AI winter in the past, and could this happen again? We will try to look at these questions and even answer them. So let's move forward. Just to re-encapsulate what we had discussed last time in a slightly different manner, we have seen that tasks such as CIFAR 10 or 100. What was CIFAR 10 and 100? You had a data set which was just of 32 cross 32 pixels, but these were colored images. So you had 3 channels, red, green, and blue. So these are typically the kind of images that we get in our CAPTCHA. And often these CAPTCHAs we see that we get in verifying that we are a human being or not, or it has been attacked by some other machine, are not just very simple for us. It is also very annoying. Remember these CAPTCHAs where you have to click the total number of traffic lights or something like that, or where you have to indicate the pixels where you see the traffic light. So this is very simple and rather annoyingly simple for human beings. But the same level of tasks, when it is given to a neural network, the amount of computational power that is required is really very large. And this is what this image is very nicely encapsulating. So let me break down this image for you. On the x-axis, you see something that we will be working with today in detail. It is called GFLOPS. So G stands for giga, FLOPS stands for floating point operations per second. So it tells you how much computational needs does a particular convolution neural network really need. So that is what is indicated in the x-axis. On the y-axis, for CIFAR 10 dataset, the top accuracy is what is indicated, and it goes from 55% right up to almost 90%. And this is where we see 3 generations of convolution neural networks. The first generation is right here at the bottom. And as you can see over here, it has very low accuracy, but also the computational requirements are quite low. Here I would introduce one more indicator that is seen in this particular graph. that is the size of the circle. The size of the circle for the different networks indicate the number of hyperparameters. As you see, this is just 1 million parameters, whereas this size or the diameter of circle indicates 150 million parameters. So this is the first generation, low number of hyperparameters, low accuracy, happening at fewer giga floating operations per second. The next generation of CNNs were the VGG networks. So you had VGG 11, 13, 16, so on and so forth. And the idea was very simple. Can we increase the parameter space, deepen the neural networks, and achieve better performance? Of course, you do achieve slightly better performance, but it is not commensurate with the large increase in the parameters and a number of operations per second. Now, the third generation of neural networks were these networks such as DenseNet and ResNet. So these modern architectures and inception variants achieve much higher accuracy with significantly lower parameter counts, but nonetheless, the amount of operations per second still is in the order of 10 to 20 GFLOPS per second. So overall, this figure highlights a very important lesson that increasing accuracy is not always about larger models, but also designing the architectures such that they balance efficiency and performance. But one thing that I would want you to recognize and remember as we enter into the next phase of our study is looking at the total number of GFLOPS that is required by a CNN to do these rather seemingly simple tasks. Now remember, when I say simple tasks, I am comparing it to the difficulty level faced by human beings. As you know, these are very simple tasks for a human being to perform. And this brings us to the key question, the first question that we had asked when we were looking at this roller coaster ride that AI ML computing has gone through. So why was there this large lull period in the 70s, 80s, 90s, right up till 2000s? Why was there this great lull period where there was a much gap between the golden period where all the ideas for AI ML computing was generated, but the application boom took quite some time to realize? And the answer comes in computational efficiency. So here I have presented to you the improvement in computational power, which is indicated in floating point operations per second as a function of passing years. So here you can see two main trend lines. The first trend line is for supercomputers, this red trend line, and the other is for desktop CPUs. So remember, 2 slides previously, we saw that the number of floating point operations per second needs to be in this particular range, close to 10 to the power of 9 or 10 to the power of 10 operations per second to do any reasonable AI ML task. So let us see when were supercomputers and desktop computers able to achieve this. And this was only possible by supercomputers in the 1990s and by desktop computers almost a decade later in early 2000s and 2005. So this is what was impeding the real life practical implementation of AI ML algorithms, that the ideas were already there, but enough computational power was only possible post the 1990s. And the second question that we will ask is, what led to this exponential improvement in the computational power? Notice that the y-axis in the first graph is in log scale. So there was an exponential improvement in the computational power. Let's see why that happened. And as you may know, this was only possible because of CMOS transistor scaling. What is the phenomena of CMOS transistor scaling? It is the ability of device engineers and manufacturing giants like Intel or TSMC to be able to reduce the channel dimensions of the transistor almost exponentially, and thereby the ability to cram in more number of transistors into the same footprint area. And as you are able to cram in more transistors into the same area, the amount of computational power that can be done by a particular chip or a particular die also increases exponentially. This is because the fundamental unit of computation, which is transistors, were becoming smaller and smaller, not just smaller, exponentially smaller. And this is what led to the Moore's law. However, this is just part of the story, as we can see in the second curve. Let us take a close look at this curve because it explains one of the most important turning points in computing history. The orange curve you see over here right at the top shows the transistor count. It is a proxy for the Moore's law. That means that the number of transistors that can be packed onto a single chip is doubling every 18 months. So naturally you would expect performance to keep rising at the same pace. But that is not what we see. Now I would like to draw your attention to the blue curve. Look at the blue curve. You can clearly see that the single thread performance, which is indicated by the blue curve, gradually rose till mid 2000s and then it completely flattened out. The similar trends can also be seen in the green curve, which shows the processor's running frequency. For decades, clock frequencies were pushed higher and higher, but after around 2005, they hit a ceiling of just a few gigahertz. Why? The answer lies in the red line. The red line indicates the typical power or the power density. So what happened is, as we made transistors smaller and smaller, they started leaking more and more current. Their dynamic power increased with frequency and the static power also increased with smaller dimensions. And Dennard's law of scaling, which is the main principle that shrinking transistors would also reduce their power consumption, completely broke down. Therefore, pushing frequencies further meant that chips started overheating and consuming far too much energy. So, even though transistor count keeps growing in modern day chips, the single core performance has saturated since almost 15 to 20 years. So, what is the way forward? Instead, as shown by the black curve, the industry's solution was adding multiple cores, multiple caches, and specialized unit to use those extra transistors more efficiently. In summary, this graph tells us why more transistors no longer translate to directly faster cores because of the power bottleneck or the power wall. And this is a critical shift that shaped the era of multi-core processor and hardware accelerators, which brings us to the extended version of the GFLOPS per second versus year comparison that we saw. In the last slide, we saw how single core performance has hit a wall because of power and thermal limits. So the natural question was, how do we keep scaling computation capabilities? The answer is given in this particular chart. As you can see on the bottom left, the CPU computation power steadily improved over the years, but only reached about 1 to 10 GFLOPS per core around mid 2000s, and this saturated. on the top, you see supercomputers, which are capable of teraflops and beyond. But please recognize that the accessibility of supercomputers is not for everybody. These machines are very rare, they are expensive, and only available to the biggest companies or to governmental or research labs. The big breakthrough then came with graphic processor units or GPUs. These were originally designed for graphics, but GPUs offered massive parallelism, something that we will discuss in detail in the next slide. Now, GPUs have thousands of cores working at the same time, and around 2010, they started to be repurposed for general purpose computing. Unlike supercomputers, GPUs were relatively affordable and available to researchers, startups, and even to students. So, GPUs have democratized high performance computing. They allowed deep learning and AI to flourish by giving compute power of a mini supercomputer on just a single card. And that is why the curve you see for GPUs takes up so steeply, hundreds and thousands of times faster than CPUs, but accessible to almost everyone. This was done by reducing the cost per floating operation per second. So GPUs were a revolution because they were able to reduce the cost of computation. And that is why we will look at GPUs in a little bit of detail. So here in this particular diagram, we have compared the GPU architecture with your CPU architecture. And the key difference lies in how they organize compute cores and memory transactions. While a CPU has only a few cores, each with complex control logic and large multi-level caches. You can see this L1, L2 caches and the shared L3 cache. This hierarchy minimizes memory latency and ensures efficient execution of sequential workloads, which are heavy in their instruction architecture. However, CPUs are optimized for latency sensitive tasks. On the other hand, if you look at GPUs, it has thousands of simpler, lightweight cores. Instead of having deep cache hierarchies, GPUs rely on massive parallelism to hide memory latency. They fetch large batches of data, perform the same operation across many threads simultaneously, which makes them extremely efficient for workloads like graphics rendering or neural network training or anything which requires the exchange of large amount of data. Apart from GPUs, there is also Google's patented technology which you may have heard of, which is called TPUs or tensor processor units. TPUs, for example, use this new concept of systolic arrays and specialized architectures for highly efficient, low precision MAC operations. Their focus is to have better power efficiency for low precision MAC operations, which is generally useful for most neural networks. However, since this will require a more rigorous understanding of computer architecture, we will not go into details. This will be a little out of the scope of our course. However, despite this big architectural difference, both CPUs, GPUs, and also TPUs ultimately face the same issue of the von Neumann bottleneck. Try to recall what is the von Neumann bottleneck. It is the limitation that computation speed is constrained by how fast data can be moved between memory and processor. This is something that we have looked in detail in our first lecture, and in case you do not remember, the von Neumann architecture and the von Neumann bottleneck, my suggestion would be please go back to the first lecture of our course and do a quick revision. So after we have done that, we can come back to the second question. Remember, the first question was, why was there a AI winter or a lull period between your development of the AI ML algorithm ideas and their practical application? And we saw that was purely due to computation power that was available. The second question that we had also asked, if this AI winter has come once, can it come again? From the high of AI ML that we see nowadays, is the trajectory only up, or can there also be the second or third AI winter? Can AI really run out of steam? To understand this, we will look at the von Neumann bottleneck once again in the context of power consumption for highly data-driven AI ML tasks. So this will be a quick recap of our first lecture of this course. As you can see, this figure represents the classic von Neumann architecture, where the memory and logic units are separate both functionally and spatially, and they are connected through this data bus. The ALU performs all these computations in the logic subsystem, while the memory unit stores the inputs and the results. The communication is what happens over the address bus and the data bus. The key point here is that this design, in essence, is deterministic, sequential, with very limited parallelism. And that is why for GPUs, you had to have many such logic units which were running in parallel. Nonetheless, these parallel units in the GPUs were also ultimately communicating with this memory block through this data bus. And that is what causes the key issue of von Neumann bottleneck, because this bus, which is shuttling data back and forth at very rapid rates, becomes the limiting factor, not just for data transfer speed, but as we will see, also for the energy cost that is required for shuttling this information back and forth. Now, when we think about AI ML algorithms, most people assume that the huge energy consumption comes from computation, the billions or trillions of multiply and accumulate operations that are performed in training and inference. But detailed analysis paints a completely different picture. And this is what is referred over here. In the y-axis, I have given the normalized energy in a log scale. Please remember, this is in log scale. And what is it normalized against? It is normalized against a single MAC operation that is happening at ALU. This is our baseline, which is marked as 1x. As we see in the x-axis, we are looking at the energy cost of shuttling data back and forth from different elements, from the ALU to the registers, the ALU to the main memory, and we will also look at ALU to the main storage. So when we see that, we recognize that moving data through the entire hierarchy quickly dominates the amount of power that is consumed during these operations, while accessing a register file costs the same as that of an ALU operation. But as we go across the chip, but as we go to the global buffer, which is nothing but the L4 or the L3 cache, the cost becomes almost 6 times. And accessing the DRAM, which is the main memory, costs 200 times more power than a single MAC operation at the ALU. And the number completely blows up when we look at the transaction between ALU and main storage, which is the NAND flash unit. This cost can be as high as 500x or more than the individual MAC operation which is done at the ALU. So in AI/ML workloads, the actual arithmetic is only a tiny fraction of the total power budget. The overwhelming majority of energy is spent simply in shuttling data back and forth. And this is where the von Neumann bottleneck shows up in practice. The separation of memory and compute elements forces constant data transfers, and that is what dominates the energy cost when you force fit AI/ML algorithms into von Neumann systems. And nothing can give you a better idea of the same when you look at the research done by the top companies. First, I present to you the case of AlphaGo. As we can see in this image, we see Lee Sedol, the Go champion who famously played against AlphaGo, Google's supercomputing system, in 2016. While the human brain works at around 20 watts of power, which is roughly the same as a dim light bulb, yet it is capable of incredibly complex reasoning, intuition, and strategy. On the other hand, when we look at this AlphaGo, we see that it relies on heavy duty CPUs, GPUs running on a large massive data center. The amount of power it was drawing from the grid was in the order of 250,000 watts or almost 2.5 lakh watts, which is almost 4 orders of magnitude higher than the human brain to achieve comparable game playing capability. So while AI matched human level skill, it also did it at a staggering energy and hardware cost. The next case study comes from IBM Research, who have also highlighted how demanding modern training can be. For example, training an image recognition model on ImageNet with just 4 GPUs can take you around 16 days and 385 kilowatts of power. If you scale this to 256 GPUs, of course, you can reduce the time to 7 hours, but the amount of energy it takes jumps to 450 kilowatts. That's equivalent to almost 3 months of household electricity consumption for Indian household. And that is only for one training run. When we move to larger scale models like GPT-3, as we will see in the next slide, the carbon footprint runs into tens or even hundreds of metric tons of CO2. So the computational needs and the power needs of AI/ML algorithms have now become unsustainable even in terms of environmental well-being. And this is best highlighted by the comparison numbers of GPT-3, GPT-4, and GPT-5. These are some recent trends. While OpenAI has not publicly disclosed the exact numbers, we can make some conservative projection based on the trends from GPT-3 to GPT-4. If GPT-4 took around 100 days of training, consuming 62 million kilowatts with a cost of $8 million. Remember, the cost is only the electricity cost. It is not the cost of having the infrastructure, of hiring people who can do these trainings, so on and so forth. It is just the electricity cost. Then GPT-5 could be easily almost 200 to 250 days with electricity of almost 150 million kilowatt hour, which is roughly equivalent to electricity consumption of 25,000 Indian households per year. So the amount of energy it requires to train your latest ChatGPT 5 model is equivalent to powering an Indian small town for 1 year. Why is this number so steep? This is because as models scale, the parameter count, the training data sets also try to grow exponentially, and inefficiencies in the memory access and data movement exacerbate the large energy costs. So even a glimpse of GPT-5 reinforces the point I have been trying to make. The largest barrier to scaling the next generation of large language models may not be algorithmic innovation, but it may be how do you power them and how do you keep up this infrastructure, which is highlighted by recent news and recent trends that you can see in the New York Times. The headline itself is very revealing. It says, hungry for energy. Companies like Amazon, Google, and Microsoft are now investing billions of dollars in creating nuclear power plants to feed energy to these AI ML tasks. Now, this is really incredible. Also, a recent feature from the journal Nature predicts that almost 21% of electricity demands will be consumed by your data centers by the year 2030. And this is totally unsustainable. And all of these unsustainable trends are because you have been trying to force fit these AI algorithms, which are inspired by biological computing, into hardware which has no relation to biology at all. And this is best highlighted in this particular graph, where we see that as you keep increasing clock frequency over the years, the power density of computation also keeps rising. This was your power wall. But if you look at where our brain is computing, our brain is consuming only 20 watts with very low power density, operating at just 10 to 20 hertz. So now the question is, how is the brain able to do that? As we have seen, today's AI systems face enormous energy and hardware challenges because they are fundamentally still built on traditional von Neumann architectural systems. In the next module, we will turn to a different question. Can we design hardware for AI that is also brain inspired? Not just software and algorithms which are brain inspired, but also hardware that is brain inspired. And to answer these questions, we will need to explore the brain's basic computational infrastructure, which is embedded in neurons and synapses. And then we can examine whether the memory device technologies we have studied in this course can be re-engineered to mimic these functions. And this will bring us to this fascinating topic of neuromorphic and brain-inspired hardware, which will be the topic for our concluding 2 modules. Thank you very much for your attention. We will see you in the next class with a new module.